Okay. For starters, we will not have class Wednesday, but I'm going to give you 2 class periods to do the homework assignment today. I would usually make it due on Wednesday, but I'll make it due on Friday. We'll cover it on Friday. But we'll get to the homework assignment today as we keep talking about graphs, or start talking about graphs. Reminder here, Acuity Tech Talk is this Wednesday night at, is it at 5:30? Let's see, a couple of different things. That's the hackathon. Here's the Acuity Tech Talk. 6 p.m. Wednesday at 6 p.m. and it's actually on Zoom. The Acuity guys aren't going to be able to make it down physically, so I strongly encourage you to attend this. This is 2 days from now. Acuity has been one of our top employers of CS students for several years. They're an insurance company up in Sheboygan, and they're not a boring insurance company. It's like the Google of the Midwest. They have like rock climbing walls there and a working Ferris wheel inside the building and all sorts of stuff like that. It's kind of a neat place. So encourage you to take advantage of that. Also, it looks like there's a hackathon thing. So the hackathon is next Saturday, and there's a sign up link for it. I think they're doing something with robotics, but I don't remember for sure. But encourage you to get involved with that as well. Okay. So there's that stuff. So let's start talking about graphs. So I'm going to mention graphs at kind of a high level, and then we're going to look at examples of a whole bunch of different kinds of graphs, but we're going to mostly ignore a lot of them is what we're going to end up doing. Part of the issue is, and I had you look at graphs during our class on Friday, and you also looked at the traveling salesman problem, which is an example of graphs, and we'll talk about that at some point as well. But the idea of a graph as a data structure is something that we use for a lot of computer science-based problems, but it's also used heavily in mathematics and several other fields, physics, chemistry. So some of the things that I'm putting in here as completeness, just so you kind of see that graphs kind of cover a broad thing, but some of the uses of graphs only apply to computer science specifically in a few cases. That isn't to say if you're writing simulation models or writing software for one of those other fields that you might not rely on one of the other types of graphs. All right. But when we look at graphs in here, when we implement our graph, which you'll do for an assignment for Friday, we're going to be looking at effectively what you can think of it as is an n-ary tree. That is a tree whose nodes can have more than 2 children potentially, with one additional caveat that a child can connect back up to other things even above the parent. All right, we'll see pictures of this here in a few minutes. All right, so it's not a tree in that it just starts at the top and expands down regardless of the number of children. You have they're called vertices in graphs, the nodes. They can connect back up, creating effectively what we might call a map. We looked at a design of a map, and that's related to the assignment. I'll show that here at the end. Okay, so this is effectively what a graph looks like. Now you can kind of consider how this operates as a tree, or could be implemented as something very similar to a tree. We might say the entry point into our graph is here at vertex 0. We could choose to say that's the case. We have to have some way of holding on to we have to have a pointer to the beginning the beginning of our graph, right? You could choose to have an array of different starting points where the pointer to this vertex and a pointer to this vertex and this vertex and this vertex. So then you can decide which, we think of this as a map, which town will we begin traveling from, something like that. But in our simple case initially, we can just say, you know what, this is kind of like a tree where the root node is this guy, and he has 2 children. I wonder what computer is connecting. Am I still online? Everybody
Yeah,
online?
you're good.
You can still hear me, okay. I just got a notice that I've signed on someplace else. I'm just wondering what other computer, my only other laptop I'm on Zoom with is my MacBook Air, and I'm pretty sure that's shut in my kitchen. Oh, Mr. Gonzalez. That guy, maybe he's messing. He tries to play his video games when I'm gone. Yeah, well, as long as we're still connected, that's all that's important. Perhaps they're just having a problem with Zoom where they're disconnecting, but we will burn that bridge later. Okay, so effectively, this could be the root node, and this root node has 2 children now, and then this vertex has 3 children, one of which actually is the child of his parent. Kind of see how that's kind of what makes it a graph, is we don't have this tree type rule. It just kind of looks like it's a tree. But when you're thinking about implementing it, especially for the assignment for Friday, you want to think about it as nodes that are interconnected to other nodes. And you may have a situation like this where this node connects to this node, and this node also connects to this node. These are 2 separate pointers. You can go to vertex 0 to 4, and you can also go from vertex 1 to 4. You can also go from vertex 3 to 4. So there's 3 separate nodes that all connect to this single node. Make some sense? All right. So computer science, graphs are used to represent a flow of computations. We might think about this like a network diagram, how the internet is kind of built, put together. Google Maps, I mentioned earlier, like, you know, in fact, really graphs are the heart of our modern day GPS implementations. All right, so certainly Google Maps is going to use things like graphs. See, Facebook users considered to be vertices, and if they are friends and there's an edge running between them, and sometimes when you go to your friends list or you go to one of your friends list, it'll show you the mutual friends, the nodes that they connect to that you also connect to, that kind of thing. So they would represent that as a graph. The internet, operating systems, resource allocation graph, where each process and resources are considered to be vertices. Edges are drawn from a resource to the allocated process. So you have a single resource like memory. So memory would be a vertex on the graph. And don't we have lots of programs that are all using system memory at the same time? So you might have 5 processes, 5 different vertices, each connected to that same memory vertex, which is a resource that all your programs are going to be using at some level. All right, so we can use these graph data structures to represent a whole bunch of different things. All right, so the next bunch of slides are going to just talk about the different types of graphs that exist. And as we get to something that's going to be interesting to us, I'll spend more time on it. But effectively, I'm just building our vocabulary. I won't test you on all of these things. I will bring attention to the ones that are interesting. But mostly this is for when you read things online or in a textbook that talks about graphs, they will use these words sometimes. So this allows you to know what the heck they're talking about. Okay, when they say something is a finite graph, what does that mean? So a graph is said to be finite if it has a finite number of vertices and a finite number of edges. Okay, well, from our generalistic computer programming perspective, we might say, well, won't all graphs have a finite number of nodes and a finite number of edges that connect them? We don't write things in infinite space, right? but we could. Nothing keeps us from creating a while true, and there's randomly generating nodes where this thing could just keep going, so we don't actually have a final graph that represents the data that we're holding. All right, but effectively I look at this, we see, oh, we have 5 vertices, 5 nodes, and we have 4 edges. That's a finite graph. Okay, whatever. As opposed to something like this, an infinite graph. Graph is said to be infinite if it has infinite number of vertices as well as infinite number of edges. When might we use this? Doesn't really matter. It's just a graph where it does not necessarily, we can't trust that it has a, that it can report to us the number of edges it might have or the number of vertices that it might have. This can be used in a lot of different areas. The thing that's popping into my mind is something called a sparse matrix. If you kind of think about, let's say you have a graph of, let's just use the United States as an example. And let's say you're trying to create a map of all the airports in the United States. Okay, fair to say there are fewer airports than there are towns in the United States, but there's still a lot of airports. Now, if you only want to have a map of the airports, that would be a map in and of itself, but it would actually be a submap of something larger. So if you really thought about creating a graph of the entire United States in terms of all of its towns and where every road is an edge between 2 places, that kind of stuff, and then you happen to have airports as one of the things, we might say that, oh, that is an infinite graph because these things, there's constant construction going on, things are continually growing, things are continually changing. But that's what they would be talking about with an infinite graph. Probably not something we'd ever run into in computer science, probably more of a mathy thing. Trivial graph, this is only interesting in computer science from a connection to a data, well, not a data structure, but an algorithm we had previously looked at called merge sort. Remember with merge sort, we talk about a list being trivially sorted, which means it's a 1 list. So sometimes when you're asking questions about a data structure, in this case, a graph data structure, being able to ask the question, is this a trivial graph, might be meaningful in whatever algorithm you're implementing. So if somebody says trivial graph, it's a graph with 1 vertex and 0 edges. Kind of put it in that same category as the empty string, that kind of thing, okay? Building block for something more might come in handy and maybe a recursive call at some point in time in your life. All right, simple graphs. Graphs which do not contain more than 1 edge between a pair of vertices. A simple railway tracks connecting cities is an example. Okay, so in this case, we have 4 vertices and we have edges between all of them, but we don't have any more than 1 edge between a single pair of vertices. A multigraph is any graph which contains some parallel edges but doesn't contain any self loops. It's called a multigraph. So a loop would be when you have a road that, well, an edge that goes one way and then an edge that comes right back. You've created a loop inside of that graph. Now, last time you would have read, I think I had up there the links for directed versus undirected graphs. So sometimes the edges between vertices inside your graphs can have directions associated with them. So if we wanted to think about a map version of that, we might say, okay, well, the road that goes between Mequon and Grafton, one of the roads is Port Washington Road. And Port Washington Road has a northbound lane and it has a southbound lane. We could consider that 2 separate edges. One is a directed edge heading north out of Mequon to Grafton. The other one is a southbound edge heading from Grafton down to, all right, Grafton. I'm only about 70% sure I'm pointing to the right place. This is the loading docks. I think it's out that way. Pretty sure that's Grafton. Okay. we have a southbound edge heading from Grafton back to Mequon. We could think about that as two separate edges in a directed graph. So technically, you then have a loop between Grafton and Mequon. That's not a good or a bad thing, it's just a thing. All right. In an undirected graph, we wouldn't define the directions of those edges. We would just say there is a road, Port Washington Road, that connects Grafton and Mequon. All right. So it's common when we talk about graphs to minimize loops, because loops, just like we maybe think about them in terms of normal programming, loops can cause problems with this idea of an infinite loop. If you are, I think I have video last class, so I wanted to look at for the traveling salesman problem. Is that correct? Okay, so traveling salesman problem is a famous, what's called an order NP problem. Really complex. And it takes a lot of time to do, which is kind of interesting because we use effectively a subset of the traveling salesman problem all the time when you use your GPS on your phone. Because when you put in and you say, I want to go from here to there in the shortest path possible, it is using a portion of that algorithm for the traveling salesman problem to get you from where you are now to where you're going using the shortest path. And that's something that we perceive happens really quickly, right? So that's something that Google Maps has done very well. But the traveling salesman problem steps that up a notch and say, hey, you're a salesman. You have, we'll just say, the towns in Ozaki County in your, I'll jump down because this is where our homework assignment is going to come up. You have the towns in Ozaki County that are in your sales loop. And let's say you live in Port Washington. You need to visit all these different towns, but also return home at night. What's the correct order to visit those towns such that you are doing it in the most efficient way possible? And you could measure efficiency and maybe in terms of gas, maybe it's in terms of time. So we would associate values with the edges between the vertices. So maybe the value between Port Washington and Grafton is a distance value. Maybe it's a time value. Maybe it's a fuel efficiency value, might be harder to come up with, but doesn't necessarily have to be distance. If you're taking rural streets to get someplace that's 5 miles away, or you could take an 8-mile long road that's an interstate to get to the same location, you very well might be able to get there quicker on the longer road because of the speed you can travel. Okay. But in any case, this traveling salesman problem effectively says, if you are a salesman and you need to visit all these towns, what's the order that you need to visit them to do your daily sales so that you've completed your job in the optimal way? All right, and there's multiple algorithms for exploring the traveling salesman problem. One of the famous ones is something called Dijkstra's algorithm. And that's actually something you will implement if you do the master's program and you take the advanced algorithms course. We write Dijkstra's algorithm in there. But in any case, that's considered to be a complex problem because we're having to take a lot of things into consideration. And imagine if you had at one of your vertices something that looped back on itself or went somewhere and then came back there. You've now maybe kind of created a hiccup where your program now just gets stuck. Like, well, technically the quickest way to get from here to here is here. But the quickest way of getting from here to this other town is through this town where you go right back. And now you just kind of get stuck in this loop, and that ends up being kind of a dead end. Kind of an interesting thing, I guess. Okay, so multi-graph, a graph which contains some parallel edges, but doesn't contain any self loops, is called a multi-graph. So in this case, and we'll actually see a similar example to this in a couple of slides, dealing with another name for a graph that this also meets the, I think it's called a regular graph. So here's an example of something with a loop. So a loop is an edge of a graph which joins a vertex to itself. Is called a loop or a self loop. All right, so something that would loop back on itself, this would be considered a loop. Also, you can have a loop where it literally loops back on itself. Probably wouldn't exist in computer sciences. I think a lot of our applications are really kind of thinking about things like maybe maps. But I suppose you could have, in fact, if we want to think about this from like a network implementation, so we think about the internet, a whole bunch of interconnected computers, right? Your computer itself has an IP address. So right now I'm connected to campus Wi-Fi. So campus Wi-Fi has handed me an IP address. But my computer also has a local IP address. Anybody know what the local IP address of your computer is? Every single computer that's running a modern operating system has a local IP address that is reachable from your computer back to itself. If you've ever seen it, it's 127.0.0.1. There's a geek t-shirt that says there's no place like home, but there's no place like 127.0.0.1. It's off the same rack as there's 2 types of people, but it's in binary, so it looks like 10. So just keep buying the t-shirts, you get all your trivia stuff. But in any case, that would be a situation where I can actually open up a network connection that goes out and comes right back to my computer using my local address. Sometimes it's called, there's a DNS name for it called localhost. That would be the DNS name for 127.0.0.1. A lot of times academically, it's called the loopback device. Okay, so if we think about our computers being part of a network, we are a vertex on the campus network, which is a graph, right? So each of our computers is a vertex on this network. Technically, from my computer, there exists an edge that comes right back to my computer, which might be interesting if I'm working on some sort of network application, like maybe I'm creating a web host or a web browser, or I'm sorry, a web server, and I want to test it inside of a web browser. I might visit localhost, or I might visit 127.0.0.1 at port 4000, and it's actually leaving my computer through the TCP/IP stack, finding that its destination is right back where we need to go, and hitting it as if somebody was external to my computer, reaching my computer. But the reason why we need to test that locally on our machines, instead of having one of you, if I had it running on here and having one of you connect, is chances are if you're in an environment like we are here, you're sitting behind a firewall, right? So I'm behind a firewall, you're behind a firewall, you put in my IP address to try to reach it. We're probably not even on routable IP addresses here. I don't know when the last time I actually looked was. I think I gotta hit option. Yeah, so we're on a non-routable IP address. So my machine is 192.168.221.133. You could probably ping that IP address and see that my computer is alive, but all my ports would be blocked probably at the router level here. Typically routers, that's the actual piece of hardware that's implementing the firewall. All right, so really my computer here has multiple ways of reaching it. I have this IP address. I have the 127.0.0.1 IP address. I have the localhost domain name, which resolves to the 127.0.0.1 IP address. All those things are edges that lead here, but they are different edges, while localhost and 127.0.0.1 would be the same edge. Okay, so if 2 vertices are connected with more than one edge, then such edges are called parallel edges. So if 2 vertices with more than one edge, let's see, if two vertices are connected with more than one edge, then such edges are called parallel edges. So like, for instance, these two guys here are connected with two separate edges. E4 and E5 here are two different roads that you could take to get from this town to this town. If you want to keep thinking about it like a map. All right. And visually, we look at this and say, oh, well, this road seems like it's better than this road. But this road might be a gravel road. This might be the interstate. So not necessarily better. Depends how you're measuring it. And we already talked about what loops are. All right. Null graph. This is something we will rarely use in computer science, but it's a bunch of vertices with no edges connecting them. Might make sense in some fields, probably not in an application that we would do in programming. Complete graph is a graph that has n vertices. Remember, vertices again are our nodes A, B, C, D. These are the vertices of this graph. It is considered a complete graph if the degree of each vertex is n minus 1. That is, one vertex is attached to exactly n minus 1 edges. If n in this case is 4, n minus 1 would be 3. A is attached to C, to D, to B. That's 3. B is attached to A, to C, to D. That's 3. D is attached to B, to C, to A. That's 3. C is attached to A, to B, to D. That's 3. So every single vertex in this graph is attached to n minus 1, where n is the total number of vertices. So it will be considered a complete graph. And ultimately, what does complete graph means? It means I can get to every other place from every place. So it's complete. Most maps would not be that way. If I jump back down to this and I think about our map of Ozaukee County, if we were to represent this as a graph, which is what we'll do for our homework, and we'll talk about this, you know, and I think I'm here in Mequon, and I ultimately want to get to Port Washington. There isn't a road that goes directly from Mequon to Port Washington. I think that's accurate. 43, you can say, kind of sneaks through, but we do hit those other towns. You hit Grafton before you hit Port Washington on 43. Okay, so from Mequon, if I want to get to Port Washington, my way to get there is I go from this vertex to either Grafton or Cedarburg. Then from Grafton or Cedarburg, I can then get to, you know, maybe from Cedarburg, I'd go to Saukville. And then from Saukville, I go to Port Washington. From Grafton, I can go right to Port Washington. Or from Grafton, I can get to Saukville. Make some sense? Okay, so, you know, we can kind of see how this map plays out. Where I won't have an edge that goes from Mequon to Saukville, or an edge that goes from Mequon to Port Washington, because in order to get to those vertices, I have to go through other vertices. Okay. This is just another example of a complete graph. In this case, there's 5 vertices. So 5 minus 1 is 4. Every node visits 4 other places. Again, complete graph. Pseudograph, a graph G with a self loop and some multiple edges is called a pseudograph. Something we probably are not going to do. Actually, something we wouldn't do in code implementations very often, but something you will actually see in the 490 class when you do finite state automatas, which is a representation of a pattern matching machine. You could have something that loops back on itself, and that makes sense. So if you had a automata that matched the language A, then any number of, then at least one B followed by C, you would go from a node A to B, and then B would loop back on itself, because you could sit there and spin matching B, 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 and then finally get to C. So that would be a formal machine, finite state automata, that gets to a matching pattern of A followed by one or more B's ending in a C at your finite state with a loop at your middle point. Let's see, regular graph. A simple graph is said to be regular if all vertices of a graph are of equal degree. So all complete graphs are regular, but vice versa is not necessarily possible. So we already saw what complete graphs are, that n-1 thing where all vertices go everywhere else. So every single one of those is a regular graph, but regular graphs, we could, for instance, if I'm looking at this guy right here, this guy goes here, this guy goes here. So that is a complete graph. I want to see, can I create a regular graph that doesn't? I could create a graph where every single vertex visits 3 other places, but it might visit the same place more than once. So that would technically be 2 edges. And so I wouldn't have visited every location. So something like this, instead of having, let's go back up to my regular ones. So I could break this real quick by just taking this edge right here, A to E, and having it go A to B, a second edge, A to B. So no longer is it a complete graph, but it is a regular graph because of the number of edges. Where the degree of a vertex is the number of edges that come out of that vertex. But again, something that's not overly important to us. This is definitely not important to us. So this is effectively something that could be subdivided into smaller components. So a graph is said to be bipartite graph if its vertex set is the set of all vertices G, can be partitioned into 2 non-empty disjoint sets. So that is 2 separate sets of vertices in such a way that each edge of our sets has one end in the first set and another end in the other set. That is, we can split. So they kind of showed the line in between them where you can create vertices. V3 goes to V2. And if this is one of our vertex sets and this is the other vertex set, V3 goes to V2. So we have one of our vertices in each of the sets with an edge going between them. V3 goes to V2. The edges are, or the vertices are in each set with an edge going between them, so on and so forth. So we can equally subdivide our graph where half of the vertices are in one half. Doesn't necessarily be half of the vertices, just some of the vertices are in one half, some of the vertices in the other half, and there are edges that all the edges go between the 2 halves. Okay, not something that's going to be anything we're going to be looking at, but does exist. Okay, labeled graph, this is helpful for us. Okay, when you think about a map, if you look at a normal Google map and you see, okay, we have I'm just going to go back down to here, and you see, oh, there's a road that goes from Mequon to Grafton. So I can go on Port Washington Road. I can go on I-43. That's another one. I could take Lakeshore Drive and kind of snake around, kind of the coast here, and then zip across over here and kind of head up. So there's a couple other roads that will let me go up that way. But when you're looking at a Google map or a paper map, not that we look at those anymore, those roads are labeled with their name, right? So we have a name of Port Washington Road, Interstate 43, Lakeshore Drive, so on and so forth. So we've actually labeled those edges to give meaning to the edges. Now, when we create our graph of this area, we might not necessarily care what an edge is called. We might not care about the road name, but we might care about the value associated with it. Maybe the value is the distance. The payload of the edge is the distance, or maybe it's the speed or the time. Maybe time's the better way of saying it. Because some roads have a 70-mile-an-hour speed limit, other roads have a 25-mile-an-hour speed limit, which you go 70 miles an hour on, which is why the neighbors complain about the Concordia people. That's why when you come off campus, you can't turn certain directions coming off campus, which will actually be interesting if you saw my post on Friday. Starting in January, the Highland Road Bridge is going to be closed because they're putting an interstate exit off of 43 onto Highland Road. So you won't be able to get to campus from Port Washington Road because you won't be able to cross Highland Road to get to campus. So your choices are to go, when you get off 43 down in Mequon, get off 43 in Mequon, you can take Lakeshore Drive up. Well, that's the road that they don't want you going on right now. When you come off campus in the main entrance, there's that sign that says don't turn left. They're going to replace that with a sign that says you can only turn left. Well, that's going to tick those neighbors off, but hopefully they, because they're going to get the exit, they'll be okay about it. Similarly, when you come out by the field house, there's that sign that says don't turn right. Later on, there'll be a sign that says you can only turn right because you have to go that way if you want to go north. So should be entertaining. Well, at the very least, that's not Concordia's fault. We probably like the fact that we have an exit. And maybe we even petition for it at some point. I don't know, but it's a good exit to have, I think. How did I get talking about that? We're talking about direct paths. Oh, labeled graphs. Yeah, so labeling edges adds meaning to our graph. Because just looking at something like this guy really has zero meaning, right? Forget about what the type of the graph is. When I look at that graph, that has no meaning to it whatsoever. Yes, I have vertices. How can I tell? Wow, they're colored green. Yes, I have edges. Well, because there's the line between the vertices. But this particular graph holds zero data. And what's this class about? This class is about a data structure. How do we structure data in such a way that is usable? This isn't usable for us. This is somewhat usable. This data is cryptic in that, okay, we have vertices named V5, V sub 1, V sub 4, yada, yada, yada. We have edges that have these values associated with them. We don't have to necessarily, they're not numbers and stuff, so we don't feel comfortable with them, but you might say, what are the values of the edges coming out of V1? And you could return E6, E5, E4, E2, E1. The data is there. We have labeled those edges, and we're able to uniquely identify vertex V1 because we've also labeled the vertices. Right? So labeled graphs are definitely going to be the types of graphs we're going to be working with. We care about the names of vertices. So for the homework assignment, our vertice names are going to be town names: Mequon, Grafton, Cedarburg, Port Washington. And the edges are probably going to be distances, because we're not going to represent every single little road that you can take out of Mequon to get to Grafton. We'll probably represent the main one. Maybe we even forget about 43. We just say, well, Grafton goes to Port Washington, through Port Washington Road goes to Mequon, which also goes to Port. And from Port, we can take the road west to get to Saukville, whatever that road's called, 33, I guess. Yeah, 33 goes through there to go from, so from here to Grafton is Port Washington Road. From here to Cedarburg is Cedarburg Road. From Cedarburg to Saukville, what is that, 143? Whatever that road's called. Grafton to Port Washington would be Port Washington Road. Port Washington to Saukville is 33 or whatever it's called up in that area. It has a different name, but that's what it is 33. But we don't really care about the names. What we care about is from Mequon to Grafton, it's 7 miles, for example. From Mequon to Cedarburg, it's 8 miles. From Cedarburg to Saukville is another 11 miles. From Grafton to Port Washington is 9 miles. From Port Washington to Saukville is 3 miles. That kind of stuff. We want to label our edges with maybe distances. That's going to be maybe the most meaningful to us. Okay. All right, so this is definitely our sweet spot, labeled graphs. We care about the payloads of our edges as well as our vertices. So really, we've added another layer of data into our data structures. Previously, when we were working with trees or linked lists or stacks or queues or any of those guys, we looked at our connections, the pointers like the left child, right child, or the next node, those pointers, and the previous node, those pointers. We didn't look at those as possible places that could hold values. They were just, I don't know, teleportation points. They got us from point A to point B through a pointer, but it didn't hold a value there. Even though we did represent them, actually, we did not represent them as edges. We just had them as pointers to the next node. Now what we will do is we're going to actually have a thing we will travel by. So to go from Mequon to Grafton, you will leave the node that is Mequon, jump onto the edge that connects Mequon and Grafton, and that edge has a value, which then can deliver you to Grafton. So you're indirectly getting to Grafton. You're still using a pointer, but as a programmer, we've now interjected the ability to have some additional information associated with that pointer. Rather than it just being a memory address, we're saying, hey, why don't you stop off in this little coffee shop? We're going to let you know that it's about 7 miles that you're about to travel. Then we'll send you to your vertex, your vertex you're going to. But on the way, you collected that number 7 because that's the distance you just traveled. We gave ourselves that opportunity to grab an extra piece of information because our graphs here will have values associated with them. Okay, so our edge is an actual object. Our vertex is an actual object. Edges have connection points between two vertexes. So an edge will have vertex A, vertex B in an undirected graph. So from we have Port Washington, that edge that goes between Grafton and Mequon. That edge has 2 vertices that connect between it. All edges connect 2 vertices. You can have lots of edges that connect more than more than just 2 vertices, but a single edge connects 2 endpoints, right? So for this vertex between the Port Washington Road vertex, Port Washington Road edge connects the Mequon vertex and the Grafton vertex. And this edge has a distance associated with it, whatever it is, 7 miles, something like that. Okay. All right, so let me talk about the homework here since we only got a couple minutes left. So for your homework, and again, this is due on Friday. We won't have class on Wednesday. I am around on Wednesday. I just have a thing going on during class time, and this assignment might be a little bit heftier thing. So if you do have questions or whatever, I am around all this week. You'll see me on campus and stuff. But in any case, so due on Friday, we're going to create an instance. We're going to create a graph data structure, first of all, a generic graph data structure. That is something that is a collection of vertices and a collection of edges with those guys linked together. You're going to have some way of saying, of building this map of Ozaukee County. So after you have your graph, you'll create an empty graph that has nothing, and you'll start adding vertices to that graph. And then you'll add edges between vertices. And you'll have to come up with how are you going to store that data inside of your graph data structure. And some of it is going to be a unique choice for some of you. You might decide, oh, I'm going to do it this way, or I'm going to do it this other way. But at the end of the day, you're going to have a collection of edges, and those edges each hold on to 2 vertices. How you want to fill up your graph with that information is up to you. But ultimately, you're going to have a bunch of edges that hold on to vertices where those vertices have potentially more than one edge coming out of them. What you don't want to do is you don't want to create duplicate vertices. Your graph should not have Grafton in it 4 times. It should have Grafton in it once, a single vertice representing Grafton that might be associated with 2, 3, 4 edges, whatever it is. Make sense? All right, so create that generic data structure, then create an instance of it and fill it up with your rendition of this map. You can decide what the distance is between Mequon and Grafton, what the distance is between Cedarburg and Mequon, so on and so forth. All right, you don't have to get into the intricacies where you say there's 7 different roads. You can assume that at most there's 1 road that you take to go from Grafton to Port Washington. If you are able to travel from Grafton to Port Washington, you can pick your road. That would be Port Washington Road, even though there's probably 3 or 4 other tiny roads you could take. That's the road. Okay, so fill it up with that. Create the edges. Submit a link to your code along with the self-assessment. It would probably be best for you to have some way of displaying it to test whether you filled it up with the right stuff, but it's not a requirement of the assignment. Okay, but I think you would have trouble making sure you did it right without having some sort of rudimentary way of displaying it. But I'm going to look at how did you build your graph and how did you fill it up. All right, questions, comments, concerns, bribes. All right, I'll see everybody on Friday.